Thin film interference is pretty cool. This is the kind of interference that allows you to see colors in soap bubbles or in oil slicks that are sitting on top of water. What's happening is that there is light reflected off the top surface, but some of the light will penetrate down into the material and reflect off the bottom surface as well. Now when those two light beams rejoin each other on the other side, back up in the, let's say the air medium, they're going to interfere with each other. This drawing is not true to what's really going on. Really the light should be coming straight down into the soap and entering at a 90-degree angle, and then coming back out also at a 90-degree angle, but it's hard for me to draw that, so I'm doing this kind of angled version. But you need to understand that it really is truly coming in 90 degrees to the surface. And again, these things always come down to an optical path length difference. One of the beams is traveling further than the other. If that beam travels an extra wavelength or a half a wavelength, we'll either get maximums or minimums. You're going to have this light beam traveling down into the material and back out. So if it does that, it's traveling a distance of 2t. That's my optical path length difference. Now, if that happens to be an entire wavelength or a multiple of a wavelength, we'll get a certain type of interference. And if it happens to be a multiple of a half a wavelength, we'll get the other. Now, which one do we get? You would think, like the two-slit interference in the diffraction pattern, that the integer multiple of the wavelength would give you a maxima, but it's reversed, and the question might be, well, why? This actually gives you a minima, and this gives you a maxima. Why is that? And it has to do with the idea of phase reversals. There is a phase change at one of the surfaces, but not at the other. Since the phase change only happens at one of the surfaces, after it passes through an optical path length difference of one wavelength, they're already out of phase. They're already canceling, and you're already getting destructive interference. The half wavelength will actually put them back together in the way that would make a maxima happen. So these are the formulas that you would use for this. Now there's one other thing that we need to add in here. The thing that's missing here is that when light enters into this other medium, it's going to change wavelength. So we actually have to modify this, and hope you didn't write it down already, but we're going to get 2nt, and the n is the index of refraction. We have to include the index of refraction because the wavelength will be smaller inside the soap or oil or whatever that medium is. Let's do a practice problem. A soap bubble appears green, wavelength 540 nanometers, at the point on its front surface nearest the viewer. What is the smallest thickness the soap bubble film could have? Assume n equals 1.35. Okay. If it's appearing green, that means we're getting a maxima. I hope that makes sense. If I write out my formula, that's going to be 2nt equals n plus a half times the wavelength. It says what's the smallest thickness it could have? Well, the smallest thickness it could have, I hope you can see, is when m is equal to 0. A bubble that gets thicker by another wavelength would still give us reinforcement of green, but we're looking for the thinnest one. So we want m to be equal to 0, and this becomes 2nt equals 1/2 the wavelength. And solving for the thickness, we're going to get that the thickness equals the wavelength over 4n. And now we just plug the numbers in. I've got 540 nanometers over 4 times 1.35. The calculator tells me that that is 100 nanometers. Now you're probably asking, why didn't you convert it to meters? Well, if you notice, I've got a distance divided by two numbers that don't have units, so it really doesn't matter what I put in. If I put it in meters, I'll get an answer in meters. If I put in nanometers, I get nanometers, and why not? So no conversion necessary, and here's your answer.